Hello everyone, welcome to this course on Software Defined Radio Hands-on for Communication Systems Design. I am Professor Suraj Srivastav from the Department of Electrical Engineering at IIT Jodhpur, and in this first lecture, we'll go through the prerequisites of this course. So the first thing is we have to work with MATLAB and Simulink. So MATLAB and Simulink installation is required at your desktop or your computer. And for this, I'll recommend all of you to use your institute account. Almost all the engineering institutes provide MATLAB, campus-wide MATLAB license. So I'll request all of you to use that account to install MATLAB and Simulink. In general, MATLAB version should not be an issue. The exercises which we are doing here, we have already verified it for different MATLAB versions, MATLAB 24, MATLAB 25, or any latest version you can use. In fact, the older MATLAB versions also are perfectly fine, and you can use any of these 2022 or 2023 MATLAB version also. The next thing is that when you install MATLAB Simulink from your institute account, then at the very beginning you will get several check boxes to select the product, and in that you can select MATLAB, Simulink, Communication Systems Toolbox, DSP System Toolbox, Signal Processing Toolbox, Audio Toolbox. So these are the important toolboxes which we will require throughout this program. In general, MATLAB Online is not recommended because those who will be working with the SDR hardware along with this MATLAB Simulink, so MATLAB Online does not support the SDR hardware. That is why we don't recommend for MATLAB Online. But still, if you want to do all the simulations, so you can use MATLAB Online also. Now, once you install MATLAB, so this I'm just giving you an introduction to the whole process, but when we will actually start the hands-on, so I'll go through these steps very quickly that time on the MATLAB Simulink environment. So when you open the MATLAB, you can launch the Simulink as shown here. There is a button in the Home tab. There is a button for Simulink. You can launch the Simulink from here. And in future, we'll require several other toolboxes to install. For example, the hardware support packages. So for that, you can use this add-on button to install the different hardware support packages. And not only this, in future, if you need any other toolboxes or packages which MATLAB supports, then you can use this add-on button to install the new packages. So as I mentioned, for SDR hands-on, we'll be requiring several other toolboxes. For example, RTL SDR toolbox, which is Communications Toolbox Support Package for RTL SDR radio, and the other one is Communications Toolbox Support Package for USRP radio, and similarly another Communications Toolbox Support Package for analog devices ADLM Pluto SDR. So these are the three SDRs for which the MATLAB support is there. MATLAB Simulink supports these SDRs, and depending on which SDR you are using for the experiment part, you will need additional these support packages for installation, and the process will be very similar as I mentioned. Just go to this add-on button and there will be a search box. You search for these support packages, type with these names RTL SDR or USRP radio or ADLM Pluto SDR, and you will get the installation button for these support packages. So you can complete the installation depending on which SDRs you have. And if you have SDR with you, then toward the end of the installation, it will ask you to connect these SDRs. So you can connect those SDRs with your laptop or your desktop and then complete the installation, the device configuration. If you don't have the SDR, then you can simply skip that step. It will still allow you to add these blocks in your Simulink models and complete the design part. But you will not be able to run it on the hardware, because if you don't have SDR hardware, you will be just able to design the model. So now with this, I will briefly introduce the course content. So let's go to the course content week by week. In the week 1, we will go through an introduction to MATLAB Simulink and supported SDRs. So I already mentioned there are 3 SDRs which right now I can see MATLAB supports. One is the RTL SDR, which is the receiver only. So this RTL SDR is the receive only SDR. Then other is USRP radio. USRP can be used for both transmitter and the receiver. And similarly ADLM Pluto SDR you can use for both transmitter and receiver. So in most of the exercises which we'll do, we'll use USRP B200 for transmitter and RTL SDR for receiver. But if you don't have RTL SDR, so you can use USRP for both transmitter and receiver, and same is true for ADLM Pluto SDR. You can use ADLM Pluto SDR also for both transmitter and receiver. So we'll first go through the introduction to MATLAB Simlink and supported SDRs. We'll install the packages. I already told you the packages. You can also get them ready. So getting the SDR setup ready and setting up the SDRs to transmit and receive signals. So we'll see that these SDRs can be used to transmit the signal over the air, and also you can receive the signal using the antenna and do the various processing. We'll take one very simple example of broadcast signal. As you know, there are many broadcast signals available in our surrounding. The best example is FM radio, and all of you know that FM has different FM stations at different frequency bands. So we'll use FM broadcast signal and we'll capture the FM signal, live FM signal, and then we'll look at its spectrum and we'll see how does a real wireless signal, the spectrum of a real wireless signal look at. Then in this week 1, we will also cover quadrature carrier multiplexing. So in short, we call it as QCM. So in general, this quadrature carrier multiplexing is basically introduced for multiplexing in the very initial lectures of communication systems. Sometimes we also call it as quadrature amplitude modulation. We can use it QCM or QAM, quadrature amplitude modulation. But you will see that the reason to introduce this quadrature carrier multiplexing is that there is a very important relationship between the quadrature carrier multiplexing and the SDR based implementation. So we'll go through the quadrature carrier multiplexing, and in the next week 2, we'll see how this QCM relates to the SDR based modern communication system design. So you'll see that there is a very close relationship between the SDR based communication system implementation and the quadrature carrier multiplexing. In week 2, we will also go through some of the digital signal processing related topics, because as you know, the software defined radio is a digital device. So will require sampling. We should know what is the sampling theorem and what are the constraints for sampling. If we don't do the sampling at the required rate, what happens? That is called aliasing. What is the effect of aliasing? Then there are several other topics related to digital signal processing. For example, upsampling. What is upsampling? What is downsampling? These will be extensively used in SDRs when we will actually design a communication system. You will see upsampling, downsampling used at the transmitter and receivers respectively. And in fact, what we'll be more interested in seeing the decimation and interpolation. That is what exactly used in SDRs. So there is a close relation between upsampling and interpolation, and similarly downsampling and decimation, and the sample rate conversion. And with the help of all these fundamental concepts, the DSP related concepts, sampling, upsampling, downsampling, decimation, interpolation, we'll see a design of FM broadcast receiver using Simlink and RTL SDR. So as I mentioned, this RTL SDR is a receive only SDR. So it can only receive the signals. It does not have a transmit port, so it cannot transmit. So we can use it for receiving any broadcast signal. In particular, we'll take the live FM signal and we'll capture the signal, the FM signal, and we will also demodulate it. And this will be the live broadcast FM signal. We will demodulate and we'll also try to listen to the original information signal coming in that FM signal. All of you already know the FM radio, so the same thing we'll do, but it will be based on our Simlink and RTL SDR based design. In next week, week 3, we'll start with amplitude modulation. So amplitude modulation is a very fundamental modulation in any communication systems course. This is the first modulation scheme which is introduced, amplitude modulation. So we'll go through what is an amplitude modulation. First of all, we'll see what is modulation, and then we'll see what is amplitude modulation, and we'll also design this transmitter and receiver for amplitude modulation using Simlink. So once we design this thing, you can verify the waveforms which you typically observe in your textbooks. In any communication textbook, you see if you have a message signal, then what will be the amplitude modulated signal corresponding to that. So that thing will verify from the Simlink model, and then we will go through a hands-on for the amplitude modulation transceiver design where we will design the transmitter part on USRP B200. This is the transmit SDR. And then we'll design the receiver on RTL SDR. And we will actually transmit one audio signal using amplitude modulation through this B200 SDR. We'll transmit it over the air, and then we'll keep one RTL SDR as the receiver. We'll process the received signal using RTL SDR followed by the Simlink model, and we will recover that audio signal. So this one complete exercise we'll do for the amplitude modulation. Then the next thing is frequency modulation. We'll understand what is frequency modulation is. We'll design its Simlink model. So this will help you understand the different waveforms which you see in the textbooks. So that is the next thing which we'll do. And then we'll design the FM transceiver using B200 SDR for the transmitter side and RTL SDR for the receiver side. And again, we'll do the same exercise. We'll take an audio signal and we'll transmit it over the air using B200 SDR by doing FM frequency modulation. And then we'll keep one RTL SDR receiver at some distance, which will receive that FM signal, perform the demodulation, and we will recover the signal back. So in all this process, you will see the theory which you study in the textbooks, the regular textbooks. You will see how that theory is implemented in the actual practice and how can we recover the signal from these modulation schemes. So this week 3 and week 4 will be devoted to analog modulation, because this amplitude modulation AM and frequency modulation FM, both of these modulation schemes come under the analog modulation. Now first I'll just briefly explain what is analog modulation and what is the digital modulation, because the next subsequent weeks, week 5 to week 8, will be covering the digital modulation. So what is the difference between the analog modulation and digital modulation? The difference comes with the nature of the source or the message signal. If the message signal which you want to transmit is analog in nature or continuous in nature, we call it as analog modulation. But if the message signal is digital in nature, for example binary in nature, then the modulation schemes which we use is the digital modulation. Now one important difference here we have to understand, whether it is analog modulation or digital modulation, the final waveform, the final output signal after the modulation is always analog in nature, continuous in nature. This we will see. So the difference of analog modulation or the digital modulation comes with respect to the source. If the source or the message signal is analog in nature, the modulation scheme is analog modulation, which is amplitude modulation and frequency modulation. And if the source itself is digital in nature, then the modulation scheme which we'll use will be the digital modulation. Another important thing is that in general, most of the real world signals in their original form are analog in nature. For example, the human voice or audio signal, they are analog in nature. So the analog modulation schemes, amplitude modulation or frequency modulations, these are ideally suited for the real world signals. Now when we come to the digital modulation, so the information signal has to be in the digital format, it should be in the binary form. If the digital signal is already in the binary form, we can directly use the digital communication systems or the digital modulation techniques. But if the signal is not in digital format, one can still convert them in digital format using the well-known sampling, quantization and encoding method. So if you do sampling followed by quantization followed by encoding, then you see that any analog signal can also be converted to a digital signal. So the digital modulation schemes basically require the message source to be digital in nature. The message source can be digital in its original form, or it may have been obtained using sampling, quantization and encoding and then in the digital form. So both of these cases you can use the digital modulation techniques. So in this week 5, we'll start with the very fundamentals of digital communications. And we'll also see what is the main reason why one can move from analog to digital. In short, the answer is that the digital communication schemes are very robust to noise, and effectively, before the signal degrades too much, you can actually recover the signal, clean it and retransmit it. So this is the main advantage of digital communication. So effectively, over a long distance, the signal remains very clean. That is not the case with the analog modulation. In analog modulation, whether it's AM or FM, these analog modulation schemes in general are not robust towards noise. But what we'll see that these analog modulations are robust toward the channel impairments like frequency offset or the phase offset, these kind of things. And because of this robustness towards the frequency and phase offset, they are still preferred in many of the analog communication systems. So in summary, the analog modulation schemes are not robust towards noise, but they are robust towards the phase and frequency synchronization. And you will see that without much investment in the phase and frequency synchronization circuitry, you can still recover AM and FM signals. But that is not the case with the digital modulation schemes. Digital modulation schemes are very much robust towards the noise, but they are not robust towards phase and frequency offsets. So we'll see that even a small phase and frequency offset requires corrections in the digital modulation scheme. So these are the fundamentals of digital communication, which we'll cover in the initial lectures of week 5. We'll see the importance of carrier synchronization for digital modulation. And then there are many other concepts like constellation diagram related to a digital modulation scheme, eye diagram. And if you want to band limit the digital transmission, then you have to use a suitable pulse shape which reduces the inter-symbol interference and also limits the bandwidth. So this is topic called pulse shaping. We'll also understand this thing because all these things will be requiring in designing a practical digital communication systems. So in general, the digital communication systems use a large bandwidth, but if you want to limit the bandwidth, at the same time you also want to reduce or minimize the inter-symbol interference, we have to use a suitable pulse shapes. So we'll go through the basics of these things. Then in the next week, week 6, we'll start with the first digital communication or digital modulation technique, which is the binary phase shift keying. So we'll design a BPSK transmitter and receiver in the Simulink model. We'll see the waveforms, and then we'll do the same experiment on the SDRs. So we'll take a text message or a digital signal, which will binary signal, which will transmit through the USRP B200 SDR as a transmitter, and then we'll recover the signal using RTL SDR, which will act as the receiver. And here you will see that you have to use all the knowledge related to phase and frequency synchronization, timing synchronization, etc., pulse shaping to design a practical digital communication system. Next, we will also try to cover another kind of digital modulation, which is the non-coherent receiver design. So as we mentioned that when we go for a digital modulation technique, then the phase and frequency synchronization is very essential, because even a small frequency offset can introduce a lot of bit error rates, right? We'll not go into all the details of these things immediately, but even a small phase and frequency offset can distort the signal. So we'll see how can we make the digital communication techniques also robust towards these phase and frequency offsets, or in general these kind of channel impairments. So we'll see the non-coherent receiver principle, and we'll take an example of differential binary phase shift keying, which we in short call as DBPSK, which is a combination of differential encoding followed by the binary phase shift keying. And here you will see that this modulation scheme DBPSK is robust towards phase and frequency offset up to a large extent. And again, we'll do the hands-on. We'll transmit a message signal, a digital or binary message signal using the B200 SDR and receive using the RTL SDR. So you'll see that with the non-coherent receiver also, we can recover the signal with much lower complexity as compared to the traditional coherent receiver. So this BPSK, when we are saying, this is the traditional coherent receiver. And finally, in the last week, we'll extend this digital communication modulation technique for the memory transmission, where you can actually transmit multiple bits into one symbol. So this is called memory transmission, and the simplest example of this memory transmission is the quadrature phase shift keying, QPSK, which is an extension of BPSK. So we'll design the transceiver Simulink model for QPSK using, first we'll design it using Simulink, we'll do the performance analysis, and then finally we'll extend this with the hands-on using B200 SDR as the transmitter and RTL SDR as the receiver. And again, you can transmit any binary message signal or any digital signal using this QPSK modulation technique. So this is the course content which we'll be covering throughout the 8 weeks. I have also listed some reference book and materials here. The classic book on communication systems is the book by Simon Hakin, Communication Systems 5th edition. So this will be mostly referring for the theory part. And there are 2 very good lectures on SWAYAM portal, the Principles of Communication Systems 1 and Principles of Communication Systems 2. These also students can refer for the theory part. And there is another set of material available on the web, which I had extensively referred for designing this course for the hands-on part. So this is the list of references. So mostly I would like to inform all the students here that mostly we will focusing on the hands-on part, and I'll keep referring the theory part where to refer. Some basic theory we'll introduce during the lecture so that you can follow the course, but if you want to understand the theory part in detail, then you have to look at some of these references. And finally, before concluding this lecture, let us also look at what are the learning objectives. So after completing this course, you will be able to design MATLAB Simulink models for various other communication systems such as CDMA and OFDM. So here we will be focusing on the design principles. So throughout this course, you will see the design principle for the communication system. And once you understand the design part, you can extend that knowledge for any other communication system design. For example, this CDMA, OFDM, these CDMA stands for code division multiple access, OFDM stands for orthogonal frequency division multiplexing. So these are the advanced communication techniques, digital communication techniques, which you can design using the principles which you learn in this course. We'll not just focus on the simulation part, we'll also connect our Simulink models with the SDR hardware for over-the-air transmission and reception. And this is very important because you will actually transmit the signal over the air to the transmit antenna of the SDR, and then you will receive it using the receive antenna of the RX SDR, and finally you will get the signal back. So we will perform the real-time baseband processing and waveform generation, and we will also analyze these live TX and RX signal, visualize the system performance, and in summary, we'll implement the complete transceiver chain and validate the link performance. So these are the main learning objectives of this course. So with this, thank you everyone. Thank you for attending this lecture, and we'll conclude here, we'll wrap up here, and we'll meet in the next lecture with an introduction to MATLAB Simulink and SDR environment. Thank you.